Okay, let's also just go over the cylindrical coordinates. That's another coordinates that we will be commonly using. If you go back to the spherical coordinates, the reason why we call them spherical is that if you just set r is equal to 0, r is equal to some constant value, the points, they form a sphere. If you just only change the angular coordinates, you obtain a sphere. Now, in cylindrical coordinates, we have a similar thing, but this time if you fix one coordinate, which we will call rho, you obtain cylinders. So consider this point. Again, just like in the spherical case, you consider its perpendicular projection on the xy plane. And there is this, its z coordinate. In cylindrical coordinates, we keep using the z coordinate. But here, instead of the x and y, we use the rho and this angle phi. So z, rho, and phi are our cylindrical coordinates. In terms of x, y, and z, well, z is equal to z. There is nothing there. X is equal to rho cosine phi, and y is equal to rho sine phi. You use the circular coordinates for the xy plane. The z plane remains at z. That's what we call the cylindrical coordinates. Well, we will be making use of these coordinates later on, probably in a couple of weeks. So I will just, if we need, we can discuss it in more detail at that case. Now I would like to discuss the Dirac delta function. Are you familiar with the Dirac delta function? Yes, okay. So let's do an example that will motivate the Dirac delta function. You remember the potential of a point charge is just proportional to 1 over r. It's a scalar function. Let's just calculate its gradient. Gradient of 1 over r. Well, this is a vector, so we have to specify. Well, since it's a vector, and we had already derived the gradient in spherical coordinates, let's use that expression. Remember, this is the gradient in spherical coordinates here. 1 over r doesn't depend on theta, it doesn't depend on phi, so those derivatives just give me 0. So the gradient of 1 over r is in the radial direction of its derivative with respect to 1 over r. Del by del r of 1 over r. And this is equal to, in the r hat, minus 1 over r squared, or minus r hat over r squared. Now, the potential of a point charge is 1 over r. The gradient of the potential should give us the electric field. The electric field of a point charge is proportional to 1 over r squared in the radial direction. So this is something that we kind of already know. Now, to calculate the Laplacian, we have to take the divergence of this expression. So the Laplacian of 1 over r, remember we had defined this as the divergence of the gradient of 1 over r, which is the divergence of minus r hat over r squared, or let's write this as the divergence of minus r over r cubed. R hat is nothing but radial position vector divided by r, its magnitude. You are familiar with Kronecker delta? So you had already said that you know the index notation. So this is equal to del by del xi of minus xi over r cubed. So this notation, does it make sense to you? Is it familiar? No? Well, let me write it this way. Well, what is the divergence of a vector field? You take the x derivative of the x component, the y derivative of the y component, the z derivative of the z component. So this is equal to del over del x of minus x over r cubed plus del over del y of minus y over r cubed plus del over del z minus z over r cubed. Let's take the derivatives. This is equal to, well, derivative of x times 1 over r cubed plus x times the derivative of 1 over r cubed. So this is equal to minus, derivative of x with respect to x is 1. This is minus 1 over r cubed plus x times the derivative with respect to x of 1 over r cubed. The second one, again, the derivative of y with respect to y is 1 over r cubed plus, no, minus y times del over del y of 1 over r cubed minus derivative of z with respect to z is, again, 1 over r cubed minus z del by del z of 1 over r cubed. This is equal to minus 3 over r cubed minus x times the derivative of 1 over r cubed will be minus 3 over r to the 4 times derivative of r with respect to x. And derivative of r with respect to x is nothing but x over r. Similarly, minus y times minus 3 over r to the 4. Derivative of r with respect to y is just y over r. Minus z times minus 3 over r cubed, r to the 4 times z over r. Well, let's see. Everything has a common minus 3 over r to the 5. So I can just take minus 3 over r to the 5 out. Well, there's another minus sign that makes a plus 3 over r to the 5. What remains is x squared plus y squared plus z squared. But that is also r squared. So it's equal to minus 3 over r cubed plus 3 over r to the 5 times r squared.
Where did these second terms come from?
This one. Or this one, or this one.
No.
No, these ones.
Yes.
Well, I'm taking the derivative of this expression with respect to x. I'm considering this as minus x times 1 over r cubed. Derivative of minus x with respect to x is minus 1 times 1 over r cubed times minus x plus minus x times derivative of 1 over r cubed with respect to x. Well, these cancels 2 of these. What remains is 0. So what we had obtained after this calculation is that the Laplacian of 1 over r is equal to 0. Take your time. Questions? Well, it's just the algebra. I mean, if you couldn't follow these steps over here, believe me, they are correct. And you can just go home and it's just taking derivatives. In a silent moment, you can just go over them, just using your knowledge of calculus, first year calculus, and you can just do them. And the end result, what you will obtain at the end of this manipulation is that the Laplacian of 1 over r is 0. Any questions up to this point? Let's do one thing. Let's consider another example containing this Laplacian. Let me consider a sphere of, let's say, radius capital R around the origin. Now, I don't even need that, but just for simplicity, let's just take this example. And let us integrate the Laplacian of 1 over R over this volume. It should be 0, right? We already showed that this is 0, so why bother? Well, let's try to show that it is 0 by some other means. Let's not use that result, but let's use some other means. Well, how we had defined the Laplacian, it was the divergence of the gradient over this volume. But we know that the integral of a divergence over a given volume, we can convert it into a surface integral. So this is equal to over a closed surface of the divergence of 1 over R dot ds. Well, what is ds? Since we are considering a sphere, ds is a vector which is pointing radially outward. So it is its magnitude in the radially outward direction. So this is equal to divergence of 1 over R, scalar product with the radial vector multiplied with ds. Well, this is just the radial component of the divergence. Well, we had already evaluated the divergence in spherical coordinates. So this is equal to d over dr of 1 over R ds. That derivative is minus 1 over R squared ds. But don't forget, we are considering a sphere now. Every point on the sphere has the same distance from the center. So small r is actually, for every point on this surface, small r is equal to the capital R. This is equal to minus 1 over R squared times the integral of ds. Well, here we have a surface integral, and remember what an integral is. Integral is always you have a region, you divide it into very small parts, then ds is the area of each one of those small parts, the magnitude of the area vector is the area, and we are summing over all those areas. It will just give me the total surface area of the sphere, which is 4 pi R squared. So R squareds cancel. So we see that the Laplacian of 1 over R, integrated over this volume at least, is equal to minus 4 pi, which is definitely not 0. Now we have a problem. On one hand, we calculated the Laplacian of 1 over R and found that it was 0. And believe me, I didn't make any mistakes in that manipulation. You can check. On the other hand, we calculate this integral, which was supposed to be 0, but it's definitely non-zero. Okay, let's try to remember your first years here. You were taking calculus courses. Okay, so you were taking the exams. You were making many solutions, and there was one place where you lost many points. Although you did everything correct, you still, in that question, you still lost some points in that question because you just forgot to mention one assumption. Do you remember it? I'm sure you have sweared a lot to your mathematics assistants because they did you so much points for not writing it down.
Closely.
No, that's close. All this manipulation is correct, but it is only valid if R is non-zero. Okay? So here in all these manipulations, we made that assumption that R is non-zero. So what we had actually found is that the Laplacian of 1 over R is 0 at any point that is not equal to 0. We don't know what its value at R is equal to 0 is, but we know that if R is non-zero, it is definitely 0. Well, this result, that the integral over the volume is non-zero, also confirms that fact. You see, the final result is independent of the radius of the sphere. You can take a sphere this size, or you can shrink your sphere. The result doesn't change. But remember, the integral is just the sum of the contributions from all different points. So if, as you change your region, the integral doesn't change, it only means that in this difference, in the region of difference, when you change it, the value of your integrand should be 0. So whatever I take the value, if I take such a sphere or this such a sphere, the value is the same. So it just tells me that in this spherical shell, the value of my function should be 0. And that is actually what we find. The Laplacian of 1 over R is 0 everywhere, except that maybe R is equal to non-zero. R is equal to 0. But then there's another problem we have. Well, you see, the integral, if you just change the value of a function at a single point, the integral doesn't change. The integral is not really sensitive to the value of your function at a single point, assuming that the value at that point is finite. Because eventually, if you just change the value at a single point, the change in the integral will be just the change in the value of your integrand multiplied by the width of that region. A point doesn't have any width, doesn't have any volume, 0 volume. 0 times a finite number is just finite, 0. So we have this function. The only difference it has from the 0 function is its value at a single point, maybe. And at that point, its value has to be infinite so that the volume of a point 0 times the value of the function, which is infinite, we might get a finite value. So we have this weird function that we call the Dirac delta. Well, this is the three-dimensional case of a Dirac delta that we will be actually using. Now let's do a simpler example of a Dirac delta. Let us look at this function. 1 if x is larger than 0, 0 if x is less than 0. I'm not defining its value at x equal to 0. Depending on your needs, you can just choose whatever you want. Let me consider the derivative of this function. 0 if x is larger than 0, 0 if x is less than 0. So just like the Laplacian of 1 over r, this function, the derivative of this step function, is 0 almost everywhere, except on maybe a single point. Well, the Laplacian, the integral of the Laplacian of 1 over r was finite, at least in a certain region. Let's see. Let's look at the integral of this one. Let's say from a to b, such that a is less than 0, less than b. Well, this is 0 almost everywhere except on a single point. But nevertheless, if we look at the value of that integral, this is theta of b minus theta of a. Well, theta of b is 1, theta of a is 0, so this is 1. So this function is such a function that it is 0 everywhere, almost everywhere. Nevertheless, it is integral over a region which contains the point x is equal to 0, is non-zero. In fact, it is infinite. If you consider the definition of the derivative, you see the definition of the derivative is at a given point, you just take its value at the next point, its value at the previous point, divide by the distance of these 2 points. If you take one point slightly larger than 0, 0 plus, let's say, another point slightly smaller than 0, 0 minus, the difference will be finite, but the difference of these, the separation of these 2 points is 0. A finite number divided by 0 is infinite. So we define this function as 0 if x is not equal to x0. That's if the argument is non-zero, then it is definitely 0. And infinite if x is equal to x0, but it is infinite in such a way that the integral of Dirac delta x minus x0 from some point to the left of x0 to some point to the right of x0, this is just 1. This is how we define the Dirac delta. Now, one example of this for example, let us define this function to be 0 if x is larger than a, and 1 over 2a if x is smaller than a. It's just this rectangular function. Now, if we take smaller and smaller value, you see the area of this function is 1, whatever the value of a is. So the integral of x dx from, let's say, minus infinity to infinity, this is equal to 1, whatever value of a is. Now, if you take smaller and smaller values of a, what you obtain is, well, it gets larger and larger and narrower. Eventually, if you take the limit, then its value at a x is equal to 0 is infinite, and it is 0 everywhere else. So Dirac delta of x is actually the limit as a goes to 0 of this new function that we had defined. Just take any function whose area below its graph is 1 and make it narrow and narrow in the limit that its width becomes 0, it becomes a Dirac delta. Another example is the Gaussian function. If you define, let's say, this delta x is equal to 1 over square root of pi sigma e to power minus x squared over sigma squared, if you integrate this function from minus infinity to infinity, this is 1, whatever the value of sigma is. And its graph looks like this one. For a given value of sigma, this is, let's say, minus sigma. Somewhere over here is plus sigma. And out of this range, it quickly goes to 0. If you take a smaller value of sigma, it becomes narrower, but higher. So this corresponds to a larger value of sigma. And in the limit, so let's call it delta sigma, if you take the limit as sigma goes to 0, delta sigma of x, this becomes our Dirac delta. You are correct, that is smaller. If you make sigma smaller and smaller, it approaches to our Dirac delta function. And in fact, just as I said, just take any function who is narrow and whose integral is 1, in the limit that its width goes to 0, it becomes a Dirac delta function. You don't have to have this step-like structure or this Gaussian structure. You can imagine a triangular structure, whatever function you can think of. Now, in electrodynamics, we will use this Dirac delta function to model our point charges. You see, when we will be talking about the densities, for example, the density of a point charge, what we mean by a charge density is you just consider a very small volume. Eventually, you take the limit as that volume goes to 0. You obtain the charge in that volume divided by the volume itself. Take the limit, the volume goes to 0. That's how we will define the charge density. Now, for a point charge, no matter how small your volume is, the charge inside that volume, at the position of the charge, will be, let's say, 1 unit. You divide it by the volume, which goes to 0. So 1 over 0, the charge density at the position of my particle is infinite, whereas the charge density at any other point will be 0. Furthermore, the integral of the charge density should give me the total charge. So the integral of the charge density should be 1. So the charge density for a point charge will just be our Dirac delta function. That's where we will be using these Dirac deltas. Now, of course, we will be working in 3-dimensional, not just 1 dimensions. So we define the 3-dimensional Dirac delta. Well, in Cartesian coordinates, it's just this function should be 0 everywhere except when r is equal to r0. And it should be infinite when r is equal to r0 such that its integral is finite. Its integral should be 1. Of course, since we are talking about a 3-dimensional Dirac delta, its 3-dimensional integral should be 1. Now, in Cartesian coordinates, it's just the product of 3 1-dimensional Dirac deltas. So this basically tells you that unless x, y, z coordinates of r and r0, they are equal, at least one of them will be 0. So the right-hand side will be 0 if r is not equal to r0. Now, if you consider the integral, over some volume, this will be Dirac delta x minus x0, y minus y0, z minus z0, dx, dy, dz. Well, x integral just gives you 1, y integral gives you 1, the z integral gives you 1. So it is just 1. And this is what we expect from the 3-dimensional Dirac delta. Definition, normalization. It will represent the charge density of a unit charge.
I have something about the mathematicians' view of...
They don't like this. They don't like that we call this a function. They call it distribution. I mean, if you want to talk with a mathematician about these Dirac delta things, don't ask them about the Dirac delta function. Ask them about the Dirac delta distribution.
Where is the actual problem? Is it about definition, interval, or something? Why is it problematic for mathematicians?
Well, you see, for mathematicians, if a function is infinite, it just means it's not defined. So they say that this function is only defined at points which does not make this argument 0. And it is 0 at all those points. So for them, it doesn't really exist. Then we come and talk about its integrals over the points in which it is not defined. Of course, they don't like it. Well, I skipped one step. Okay, we define this Dirac delta. Okay, this is the Dirac delta in Cartesian coordinates. But what about the integrals? I mean, strictly speaking, Dirac delta, they don't really make too much sense on their own. But they make sense when you multiply them with some function. So let's say, let's go back to the one-dimensional case. This is our Dirac delta. Let's multiply it over x and integrate over x from, let's say, a to b. These integrals are well defined. I mean, if you ask mathematicians about and talk about this thing as a distribution, they will be happy. They will talk about this integral, etc. They will not complain. Now, let's consider some cases. You see, let's say this is the point A, this is the point B. Now, x0 can be somewhere over here, or it can be somewhere over here, or it can be somewhere over here. We have to specify 3 different cases: in this region, or in that region. You see, this is an integral. Again, let's remember the definition of an integral. The integral is just a sum. You just give x value in the range from a to b. You just give x values in this interval and sum the contribution. Okay, that is what this integral is about. Now, if x0 is in this region, then x, remember, takes values only in this region. That is, x is larger than a. If x is larger than a and x0 is over here, it just means that in this region, x is always larger than x0. But if x is always larger than x0, then this number over here is always positive, and the Dirac delta function is always 0 if its argument is positive. So this is always 0 in this interval if x0 is less than a. Well, just integrating 0 just gives us 0. So that integral is equal to 0 if x0 is less than a. Well, more or less, we can do the same analysis if x0 is over here. Again, x takes only values between a and b. That means x is less than x0. If x is less than x0, then this number is always negative and it is never 0. If it is always negative, then the Dirac delta is always 0 in this interval. Well, it's just we are integrating 0 over some finite interval. That gives me, again, 0. Then first let me write the answer in the other case. And now let's see why. Well, we know that x0 is somewhere between a and b. So let me split this integral into 3 parts. From a to the left of x0, plus from the left of x0 to the right of x0, plus from the right of x0 to b. Now, in this integral, x0 is not in this range between a and x0 minus. So this integral is just 0. Similarly, if you look at this integral, x0 is not in this range. So we had already seen that if you go look at over here, we had already seen that if x0 is not in this range, that is, if in this range the argument of the Dirac delta is never 0, then the integral is 0. Here, x0 is not in this range because x0 minus is a number slightly smaller than x0. x0 is not in this range because x0 plus is slightly larger than x0. So these two integrals are 0. The only non-zero part is over here. But again, here, x0, the difference between x0 minus and x0 plus is infinitesimally small. They are very, very close to each other. We are talking about a very narrow range. Eventually, we will take the limit that narrow range goes to 0. But if f of x is a continuous function at that point, it just means that in a very, very small interval, its value doesn't change at all. So it is just constant in this interval. Well, if it is constant in that interval, then this is equal to f of x0 from x0 minus to x0 plus dx Dirac delta x minus x0. But the integral of Dirac delta is just 1. Of course, before we were always mentioning from minus infinity to infinity, but it doesn't really matter because from minus infinity up to x0 minus or from x0 plus up to plus infinity, Dirac delta is 0 anyway. So this is equal to f of x0. This is if x0 between a and b. Okay, Dirac delta is a weird function. Usually it's quite confusing at the beginning. It's almost everywhere 0. But the nice thing about the Dirac delta function is its integral is almost trivial. It just tells you that wherever you see x in the integrand, put x0. No, this is 1. What was the definition of the Dirac delta? So it is 0 almost everywhere, except then at the point that makes its argument 0. And its integral over an interval that contains that x0 is 1. That is how we define the Dirac delta. So that is why here this integral is 1. Its integral, you see, just imagine it as a rectangle whose width is 0, height is infinite, it is 0 times infinite. If you consider it as a limit, 0 times infinite is an uncertain limit. So you have to do some other means to take that limit. Now this Dirac, in the definition of the Dirac delta, we are considering this limit in such a way that the product of 0 times infinite is 1. For example, if you go back to this example, instead of this 1 over 2, you can just put 1 over a. In the limit a goes to infinity, a goes to 0. Again, this is 0 almost everywhere, infinite here. But if you choose the height to be 1 over a, it's not the Dirac delta. It is Dirac delta twice the Dirac delta. So the crucial point is that its integral should be 1. That is a defining property of this Dirac delta. If you have a function that has similar properties, 0 almost everywhere except on a single point, and the integral over that point, over a region that contains that point is, let's say, 5, then your function is not Dirac delta, but your function is 5 times Dirac delta. Yes. How you take the limit is determined by the definition of this Dirac delta. Its integral should be 1. That is the definition. You have to take the limit in such a way that the area below your curves is always 1. Or it becomes 1, let's say, in the limit. Let us also consider one more case, the Dirac delta in spherical coordinates. The three-dimensional Dirac delta in spherical coordinates. Again, what we want to consider is this one, r minus r0. And if 2 points are equal, then their coordinates have to be equal. That's the definition of the coordinate. Given the coordinates, the point is unique. So if r and r0 has the coordinates r0, theta, theta 0, phi minus phi 0. So we kind of have to have these Dirac deltas, all three of them, to make sure that unless these 2 points are equal, the left-hand side is 0. If you look at the right-hand side is non-zero only if the magnitudes of r and r0 is equal to each other. The theta angle of those two vectors are equal to each other, and the phi angle of those two vectors are equal to each other. And if r, theta, and phi coordinates of two vectors are each other, they are equal to each other. Now, but of course, in general, this is just one condition. We know that the Dirac delta has to be 0 if the argument is non-zero. So both the left-hand side and the right-hand side, they satisfy this criteria. But if we multiply it by some number a, they still satisfy this criteria, that they are 0 if their arguments are different. The second defining criteria of the Dirac delta is their integral. So the integral of r minus r0 dv, let's consider all over space, over all space, this should be 1. Now the volume element in spherical coordinates, do you remember? What is the volume element in spherical coordinates? R squared sine theta, d theta, d phi, dr of a Dirac delta r minus r0, theta minus theta 0, phi minus phi 0. This integral should be 1. R goes from 0 to infinity. R0 is somewhere in this range. So the integral, if you remember the integral of the Dirac delta function, if we integrate over r, this is just a single Dirac delta function over here. This just tells me that wherever I see r, I should put r0. So this is equal to that is equal to r0 squared. That is the r integral. That's it. If I take now the theta integral due to this Dirac delta tells me that wherever I see a theta, I should put theta 0. Sine theta 0, I took the theta integral. Now the phi integral, well, there's no phi dependence, nowhere, so the integral of the Dirac delta is just 1. What is left is a. So a should be 1 over r0 squared sine theta 0. So in spherical coordinates, Dirac delta cube, the three-dimensional Dirac delta, is not just the product of 3 Dirac deltas, it is the 3 Dirac deltas divided by this expression over here. Or you can also just divide it by this expression over here, r squared sine theta. That is the coefficient of the volume element. You have to divide it by this one, to make sure that the other defining property, that is the integral of the Dirac delta, should be 1 holds. If you don't multiply it by this factor, then the integral of the product of these 3 Dirac deltas over the whole volume is not 1. No, there's no divergence over here. This r squared sine theta. This is just the volume element in spherical coordinates.
Hocam niye fiil alakalı bir şey sonuçta?
Well, it's mainly because there is nothing that depends on phi in the volume element, except that d phi. You see, this factor over here is actually this factor over here.
Ama d var, bunun etkisi mi?
No, these coefficients. You see, the integral of d phi of the Dirac delta is already 1. When you take the integral, nothing remains from the phi integral. But there is an r0 squared that remains from the r0 integral, r integral. So we should cancel that one. So that is why we divide by r0.
In what the situation we choose to add the as endpoints, so what's the corresponding limitations in 3D space?
Here. Well, here, let's say, one reason why I consider the all of space is, let's say, we can consider Dirac delta cube r minus r0. Let us multiply it with f of r, integrate over a volume. This is equal to f of r0 if r0 is in my volume. It is 0 if r0 is not in my volume. So this time I'm integrating over some volumes. Let's say if my volume has this shape, my r0 is over here, then this integral just gives me 0. Because the argument of the Dirac delta is never 0 within my volume. Any last minute questions? Okay, then see you on Tuesday. Tuesday in this classroom again.